Our next speaker is Haruka Kusakabe. She's a postdoc at the University of Geneva, and she's going to be talking about Lyman alpha halos.
Thanks for the introduction and organizing this wonderful conference and giving me an opportunity to introduce my work here. As a part of talks on HGNOs, I will introduce Lyman alpha halos around UV-selected galaxies at redshift 3 to 4 as a CGM tracer. The Circumgalactic medium, CGM, is a gas surrounding galaxies and regarded as a source for galaxy star-forming fuel. The gas is exchanged between the CGM and the ISM via inflows and outflows. The CGM has radiative transfer effects on ionizing and Lyman alpha photons, so it is important to study the CGM not only for galaxy evolution, but also for reionization. The CGM has been observed with absorption imprinted in the spectra of background pressures, such as damped Lyman alpha system and Lyman limit systems. The CGM is also observed with emission lines. However, the direct observations with 21 cm emission are only possible at very low redshift. At higher redshift, Lyman alpha, magnesium-2, and carbon-2 are used for tracers. These observations in emission allow us to literally take picture of the CGM. In particular, among those tracers, extended Lyman alpha emission called Lyman alpha halos have been commonly investigated. The key question in this study is, do UV-selected galaxies generally have a Lyman alpha halo? Historically, Lyman alpha halos have been studied with stacked narrow bands targeting Lyman alpha emission around Lyman alpha emitters and Lyman break galaxies in overdense region. Recently, IFUs like MUSE and KCWI make it possible to detect individual halos. So statistical property of Lyman alpha halos of Lyman alpha emitters have been studied, and now we know that Lyman alpha emitters generally have a Lyman alpha halo. However, it has been confirmed with MUSE that Lyman alpha emitters are only a small fraction of UV-selected galaxies. Therefore, we need to avoid sample biases towards bright central Lyman alpha emission, Lyman alpha emitters, and or overdense regions when we study Lyman alpha halos around galaxies. So in this work, we use MUSE data from MUSE Extremely Deep Field Survey, MXDF. The MXDF aims at the deepest MUSE air observations. Within the radius of 31 arcseconds, the integration time is from 100 to 140 hours. The MXDF is located in the XDF and overlapped with the MUSE Hubble Ultra Deep Field Survey. The data reduction is based on the MUSE pipeline with a number of specific developments and improvements. The surface brightness and the flux limits are like these values, and thanks to these unprecedented depths of MXDF, in Bacon et al. 2021, we detected the cosmic web filament with Lyman alpha. The MXDF catalog was created by MUSE team and includes more than 600 sources. And our sample was first selected from the Rapersky HST catalog with the criterion of an apparent magnitude cut at 27.5. Out of 142 galaxies, 96% of the galaxies have a Spec-z in the MXDF catalog, and UV continua of the remaining sources are detected in the MXDF data cube. Among them, 21 galaxies were confirmed to be in the redshift range of our interest, 2.9 to 4.4. 6 sources are also included in the previous MUSE halo study in Regular et al., and 15 sources are newly selected for our sample. The UV magnitude and redshift of our sample are shown in this panel. And as shown by a green rectangle, we also have a UV magnitude limited subsample with 11 galaxies. In the sample, we also have a group or pairs of galaxies at redshift 3 with very extended surrounding Lyman alpha halos. Some of the galaxies show Lyman alpha absorption and strong Lyman alpha emission. There are 2 of the LA overdensity with cosmic wave confirmed in Bacon et al. Those sources may live in different environments, therefore we calculated Lyman alpha halo fractions for all sources, including them, and only for isolated sources. To test for the existence of halos, first of all, we optimized Lyman alpha narrowbands and obtained curve of growth radius and inner radius. Next, using the main target mask and the neighboring object mask, we measure the signal to noise of the flux between the inner radius and the curve of growth radius. We tested a null hypothesis that the source does not have more extended Lyman alpha emission than the PSF convolved HST continuum-like component. We check the deviation of the surface brightness profile from that of the PSF convolved continuum at the outside of the main plate of the galaxies. Those panels show the Lyman alpha surface brightness profiles and result of the halo test for individual galaxies. All of 6 Lyman alpha halos included in Leclerc et al. Were confirmed to be significantly extended. For 15 new sources, 11 halos were confirmed. So in short, we obtained 70 Lyman alpha halos and 4 non-Lyman alpha halos. As you can see here, some of the new Lyman alpha halos show various profiles, including Lyman alpha absorption at the center and complicated bumps on surface brightness profiles. In this diagram of UV magnitude and redshift, Lyman alpha halos are indicated by red circles. And here, example of Lyman alpha halos. The top left object has little absorption at the center and very diffuse extended Lyman emission boundary, while clear central Lyman alpha emission are seen in other sources. 4 non-Lyman alpha halos are shown here. We performed the completeness simulation for each non-Lyman alpha halo to estimate potential halo parameter sets that cannot be confirmed even with MXDF. And with these all sources, we calculated Lyman alpha halo fraction at 80%, as shown by the left gray bar. The fraction remained high even when we derived it for the UV magnitude limited subsample, shown by green bars, or even when we limited sources to isolated galaxies, shown in the middle column. Those fractions are similar to that for MUSE Lyman alpha emitters in Leclerc et al. And the high fractions imply that high star-forming galaxies generally have a significant amount of cool or warm CGM gas reservoir. In fact, any halo origin requires surrounding cool or warm gas. It has been expected from low G CGM observation, high G absorber observations, and simulations. At higher redshift, gas gets denser and more neutral as a result of increasing rates of coagulation and the higher mean density in the universe. So the high Lyman alpha halo fraction has been predicted, and for the first time, it has been confirmed with our UV-selected sample and MXDF data. It is also very interesting that 4 sources do not show a significant Lyman alpha halo. The top left source is a potential Lyman alpha halo with anisotropic Lyman alpha profile, like a bipolar, but the emission is too diffuse to be confirmed with circular surface brightness profiles. The top right source is the most interesting source to me. It is a strong Lyman alpha emitter with a 125 angstrom equivalent width without halo. So it may imply a poor amount of the CGM gas and may help Lyman continuum to escape to IGM. The bottom 2 sources have a weak Lyman emission at the center, implies that Lyman photons get killed in the ISM and the CGM, and then the halo-induced mechanisms may not work for these objects. Next, we calculated the mean Lyman alpha surface brightness profile of Lyman alpha halos with cosmic dimming fractions. The mean profile of 17 Lyman alpha halos is 2 times brighter than the surface brightness profile of MUSE Lyman alpha emitters in Vysotsky et al. But this could be explained by the difference in the sample selections. We obtained a typical Lyman alpha halo size above the 1 surface brightness limit at 40 physical cube/sec. The size can be used to estimate the incidence rate of Lyman alpha halos, which allow us to connect the H1 gas observed with Lyman alpha emission and the gas observed with Lyman alpha absorption, such as DLAs and sub-DLAs. Here, we assume that Lyman alpha emission traces cool or warm gas, and that the Lyman alpha halo size is 40 physical cube/sec on average. The incidence rate of Lyman alpha halos is given like this formula, with the number density from a UV luminosity function and the Lyman alpha halo fraction. The incidence rate of Lyman alpha halos for UV magnitude brighter than -18, our faintest limit is 0.76. This high incidence rate implies that almost all the sky is covered with Lyman alpha emission of galaxies from redshift 3 to 4. Moreover, this value is in between the incidence rate of damped Lyman system and some damped Lyman systems. We extended this exercise to higher redshift and fainter magnitude with assumption of halo size and number density from luminosity functions. The abundance matching for DLAs incidence rate requires fainter UV magnitude at higher redshift, and the same trends are found for sub-DLA and LLS. This trend can be explained by the redshift evolution of the absorber's incidence rate and the UV luminosity functions. And here is my summary slide. Thanks for listening.
All right, thank you very much. We'll wait just a little bit while people write their questions. All right, so we have our first question about the Lyman alpha halo galaxies you've looked at. Are they associated with clusters or groups?
So not always associated with cluster or groups. As introduced in Vacon et al. 2021 in the MXDF field, there are several LA over density, but it's not like a proto-cluster level. It's like a group of Lyman emitters. And we found a high Lyman halo fraction for those sources. But we also found a high halo fraction for isolated galaxies. So not always associated with massive structures.
Okay, thanks a lot, Haruka. There's another question about the typical scale length of the halos that you find.
Scale length, a good question. I measured it, but I don't remember the typical value now. And it is a bit larger than or similar to LLEs in Florian studies. It was not a crazy value. And I can give the value later after the talk.
Yeah, exactly. You can always go to Slack. Okay, there's one more question. The question is, do you find any redshift evolution?
Next question. I'm also interested in it. And for the moment, our sample is very limited with 21 sources, so it's very difficult to check the redshift evolution. But within our sample, at least we don't find any significant evolution. And in the future, we plan to apply our Lyman alpha halo test for 40 galaxies in the MUSE Ultra Deep Field sources and the upcoming Muscatel sources. So our sample size is several hundreds, so we can check the redshift evolutions in the near future. Thank you.
Okay, great. Thanks a lot. Thanks, Haruka.